And we're good to go. All right, so hello everybody. My name is Harri Ruuttila. I'm coming from Palo Alto Networks. That's the company I'm representing today. My title is quite long. I don't want to read it out loud, but basically I deal with our products which are doing behavioral analytics and how can we use that to detect attackers which are already in your network and insider threats trying to cause you harm. So basically, the first question I want you to ask yourself is that if somebody is already in your network, could you see them? And think about it. I say that many companies think about this, but they don't have actually the tools or the processes to do this. Today we will give you some tools to do it. And sometimes if you're able to do it, it takes a long time, like hundreds of days to figure out that, okay, somebody was here. So let's look at how can the tools also help you on that end so it's a bit faster. If we look at a successful attack, it requires multiple steps. This is what we call a attack life cycle or a kill chain, whatever you want to call it. But we can split it into two parts. The first part is the first three parts happening here. What's common on these ones is that's usually very fast. It happens in minutes or seconds. It's very fast to do an exploit and install a malware if it's successful, and then just do a CNC callback to the internet. It's usually requiring very few actions on the network, and most cases these can be detected and prevented when it's known by some sort of IOCs, meaning indicators of compromise. The latter part of the ladder 3 over there, these are the ones that we usually don't focus too much on because it's quite hard to find the so-called needle in the haystack, because on the ladder 3 part, the attackers are usually already using valid credentials. They're using the same tools as your IT admins. They're using the same tools as your normal users to roam around the network to figure out where the data is, what they actually want. This can take days, weeks, or months. As we look at the reports from different vendors or Verizon or what kind of other reports there are, it can be even hundreds of days to figure out that now there's actually an attacker in my network and how can I detect them out there. These can rarely be identified by IOCs. The command and control there in the middle, it's kind of divided into two parts, but I'll give you an example of a CNC also, which is quite hard to detect by IOCs. And usually it requires large number of different kinds of network activities, like starting from port scanning and connecting here and there, and then roaming around the network, compromising other hosts, or if getting credentials, moving to other hosts, etc., etc. But it usually requires a large number of network activity to roam around the network to find the data they are actually after. So let's focus today on the ladder 3 part. Palo Alto Networks does a great job on the first 3 as well with our next generation firewall and our Traps endpoint agent. But today let's focus on the ladder 3, which was the topic of this discussion. Let's look at some examples first. Well, everybody knows about this, NotPetya one. This is the data center of the company that was doing the software called MeDoc, where NotPetya was launched. Why I wanted to bring this up was that if the companies which were actually hit by NotPetya, the Viper malware, would have had some sort of behavior detections in place already when the MeDoc software allegedly was used for spying on those organizations, they would probably have seen the difference in behavior and would have been able to detect that already before the NotPetya Viper was launched. Second example, Fish Tank. This is coming actually from US. It's a casino in the US which had an attacker in their network. Now the casino had very good defenses already in place, and the attacker was having a hard time exfiltrating data outside the casino network. But for the attackers, it was a good chance for the attacker because the casino cared about its guests, and they actually put up a really nice fish tank into the casino, and it had some IoT device in the tank to control the climate or the environment inside the tank, and it was connected to the network. So the attackers actually found out this thermostat on the fish tank, and they used that actually to be the pinpoint where they started exfiltrating the data outside the network. Now the casino fortunately also had behavior-based detections in place, and they actually found out that why is our fish tank thermostat suddenly transmitting gigabytes of data outside of our network, and they actually caught it by that way. But the only way they could have seen it was the change of behavior. And the third example I have here is CNC. So it's a Twitter-based CNC. This is actually allegedly relating to a North Korean APT group. They created a Twitter handle called that and actually put up a nice picture of a really popular South Korean singer there, but all her tweets are gibberish. That's gibberish to us, but that actually is the CNC commands for the malware, which is now beaconing outside the customer or the target networks to Twitter to read her tweets and act upon these tweets. The problem with this kind of detection with normal IOCs is that, is this actually a user going to Twitter, or is this actually a malware now looking at Twitter for instructions? So kind of hard, but with behavior-based solutions, we could have probably figured out that, okay, now somebody's periodically going to Twitter, which is abnormal for a human, but for a machine, it's a bit more common. This isn't the only one. We have seen similar ones going to Google spreadsheets, for example, Microsoft TechNet, etc. So this is the new CNC channel, using some sort of an application that your users are also using. It's impossible to figure out this by static IOCs. You need something more. So the 3 reasons why usually companies don't catch the attackers that are already lurking in the network is that they can already have legitimate credentials and use the legitimate software. So they look like your users. Second reason is that you focus still on the malware part, the first 3 parts. You put your money there, that's where we have been familiar putting the money and effort in buying a new antivirus or buying a new hardware firewall or some signature updates to it. It's good for the first 3 parts of the attack chain, but for the lateral movement and exfiltration, it's not so good anymore. And the third one, I think it's very important as well. I will actually cover this one with an example later on today. The security teams are so overwhelmed with alerts that they don't know what to focus on. They have a tidal wave of alerts coming at them that they don't know what to focus on to find the actual things that they need to find. So why isn't the current approach working? First of all, we collect the wrong data. By wrong data, I mean we collect too few data, too low amount of data. Usually what we collect in logs is the violations. You collect your logged connections from your firewall probably, some alerts from your IPS sensors, some alerts from your antivirus sensors, but those are all denied connections or violations. And then the other reason is that we don't have sensors in all of the places that we need. A lot of companies only see north-south traffic outside their network, but they don't have any clue what's going on east-west. They don't know how are your clients talking to the data center, etc. So you're blind to the threats spreading inside your network. So this is the first problem. The second problem relates closely to the first problem, is that it's either related or continuation of it, but lack of scale. As we are accustomed to on-prem solutions with SIM solutions, they are hardware-based, they have a cost, and maybe it's good enough for you today to collect all your violation logs, but maybe tomorrow if you want to collect more, you need to buy more hardware, so it doesn't scale. On the other hand, it has very slow software release cycles, so they don't get updated every day or every month even, they get updates even further. And the licensing usually for an on-prem log collection / SIEM solution is based on events per second. Now, when you think about the first one, you're forced to collect only your violations, so then your events per second is quite low, so you can afford to buy the hardware which is able to get it into the system, and you're afford to buy the licensing for that system because it's usually licensed by events per second. But this is actually totally wrong. You should do it all the other way around. I'll get to that in a few while. Once you get actually your stuff into that system, it usually has statically built correlation rules, built by you or the vendor or your service provider, but a human. The human builds them. The problem with this one is that they're hard to develop and maintain. You need to think about it, but you probably overlook something. And when you have developed it, it stays like that. It's static. It doesn't evolve over time. It always stays the same. And that's why it's false positive prone. So during the time it's there, it's not evolving at the same speed as the attackers are evolving. This leads to slow investigations, which means that it's a repetitive process. You need to do it. You need to stitch around what happened on the network, what happened on the endpoint, what happened here and there, look at different logs. Takes time, and it's very manual. So it usually can take days or weeks to actually block the threats with this. The beauty of this slide is that you can read it from left to right in sequence, or you can read it from right to left. It also applies that way. So the reason we have slow investigation is that we have very static rules which are hard to maintain with lack of stale and wrong data, or the other way around as I just read it. So how can we fix this? First of all, we need to gather a lot more data, rich data. We need to collect data from the network, east, west, north, south, everything. We need to collect data from the endpoint, user, process, context, etc. And from the cloud, what's happening there as well, with very rich logging. So when we have that done, and we want to collect all the allowed stuff, because that's what's interesting to us. What was denied, that's already taken care of, but what was actually allowed, that's the most interesting one. So you can guess that the amount of logs we now gather with very accurate logging is actually very, very much higher than with just the denied logs. So that's why we need to be very scalable, and that's why we have actually utilized cloud here to store the logs. As we store the rich logs in cloud, we have the elasticity needed to scale when needed and add more storage space, and of course rapid innovation speed in the cloud. We can push updates into the software every day if we wish. If we have seen that we need to add some detectors or something, the cloud gives us this ability. Naturally, we use machine learning here to figure out what's normal and what's not. The computer is very good in these ones, a lot better than the human brain. We'll do an exercise in a few slides that we can profile what is normal and what is not, and automatically alert and take action based on the fact that if somebody's behaving out of ordinary. Then this leads to more rapid response. I'm not saying immediate response, but more rapid response instead of days and weeks to hours. So then we have the context from the network and the endpoint and the cloud to small number of actionable alerts, which we can then investigate more and take action with remediation through our platform. So let's do a bit of an exercise. I want all of you to close your eyes for a moment and then picture your computer. Then in the morning when you open the computer, picture all the applications you start using. You probably open your web browser, you probably open your email program, some other things. And during the day, picture during the day, what kind of connections do you use? Some SaaS services here and there, your email, other things. Probably you could do some instant messaging, chat, Slack, Microsoft Teams, whatever. So there's a lot of connections coming out of your computer and where they're going. Then picture that if this was the amount of connections for your computer, picture all the other employees in the same company that you work for, and the same thing for them, all right? And then add all the servers, what kind of connectivity is there, where are they talking to, and then add all the remote workers, and then add all the IoT devices, mobile devices, even the coffee machine in the cafeteria, because it's connected to the internet nowadays, of course. Where are they talking to and how? How are they talking there? How much data they're transmitting? In what kind of intervals? What kind of methods they're using in the protocols, HTTP, POST, GET, etc. What kind of URLs they're accessing, with what kind of cycle, and so forth. Now, when you have pictured this is a snapshot in time, then picture that you record this information for a month, all the connections, what's going on, and add information from the endpoint side. What are the users on the computers? what kind of programs they're launching, which causes the connections to go out, and in what context. And when you have pictured this for a month, then you are where we want to be. Then you have actually built out the baseline for a single computer, but then you start comparing that single computer's behavior against its behavior through the 30-day history and its behavior against its peers. The cafeteria coffee machine against the other coffee machine, the server against another server, your workstation against your co-worker's workstation. So that is what actually Magnifier does. So Magnifier is the name of the product I'm here to discuss with you today or represent. And it starts with the green logging layer or the enforcement layer of network, our next generation firewalls, endpoint, our endpoint products, cloud, our VMs in the cloud. We gather the rich data, transmit it to a large data lake in the cloud, and from the cloud we can bring you this new kind of functionality without you having to install another box or another agent just to do this one thing. So when you pictured that, you can grasp the multitude of information and the problem there, but with machine learning we're actually able to do that very efficiently. So let's look at an example of Magnifier in action. So port scanning. Port scanning is a boring problem. Nobody wants to look at port scanning, but port scanning usually comes from 3 different sources. It's coming from authorized applications, so your applications are looking for new hosts or new services or new vulnerabilities in the network. IT admins figuring out that what is this endpoint now doing or what is it in your network, or malicious actors. Usually they want to do port scanning to figure out what is in this network and where do I go next. Port scanning is just one of the tricks they do or could do. The problem with port scanning and legacy systems is that the legacy approach doesn't work. Usually you created a rule that, okay, if I see connections to over 10 ports in a certain amount of time, alert me, or 20 ports, then block it. All right? When the user gets this kind of an alert, blocked by port scanning, okay, the user gets to decide what to do. But the problem here is that if the user actually reads through that, it says, if you're experiencing issues connecting to other devices in your network, such as printer. So what do? They usually press stop blocking. I still want to print stuff. All right? So what happened there? You're actually don't caring about port scanning anymore or not blocking it. And what actually happens is that you get so much of these in an legit network that what do also? Do not notify me. So basically, you just discarded all port scan information and nobody cares. Well, let's look at a case we had. We had a case in a company that had 40,000 hosts, so a big company. But for 3 days, we looked at their logs just for port scanning, and we saw that there was over 42,000 port scans in 3 days. 105 sources to almost 22,000 destinations. So you can figure out that if in 3 days there's over 42,000 port scan alerts going to your SIM system as you're logging the suspicious ones, what is the SOC analyst going to do about this? Well, absolutely nothing. He has a bunch of other alerts to look at, and port scanning is not something you want to look at because it's usually false positive and not interesting to you. But it's something that you shouldn't overlook. But let's look at how the product actually works here, and everything is actually happening automatically without user interference. I'll tell you when the user gets into the picture. So first of all, we grouped, or the product actually groups, the IP addresses to actual individual hosts. So we got down to 86 hosts and approximately 19,000 destinations. So still unmanageable, all right? Then as we do the profiling, we create the source profiles for all the hosts and the destination profiles for all the hosts in the network. We can then uniquely say that as we put it in a table, that's the unique identifier for a host, and then there's the destination scanned and the active days, we can show it like this. And this is actually happening automatically. You never see this, but this was basically what the product does for port scanning. Then as we see it over time, if we put these scanners in a graph, it's more obvious to us. So these guys over here, these are the aggressive scanners. So they scan almost every day, multiple hosts, some of them over thousands of hosts, so quite a lot. And these guys over here, they're more periodic ones. So now and then, every few days, they scan multiple hosts. So we can see that we have the long history in the profiling, so we can see that. So most likely, these guys are legitimate, but they cause 99% of that noise. But as the product utilizes the profiling and machine learning, we're able to say that these are most likely benign, legitimate. It might be a very noisy attacker in that mix, but doubtful. But still we have these guys to worry about over here. So let's apply a bit more machine learning magic into this one. As we look at the 14 scanners that we saw over there, there's guys like Landsweeper, Nessus, Rapid7, Forest Scout, probably totally legitimate stuff, and they're scanning the network. After we eliminate these, we are left with 72 sources, 105 destinations, and only 186 scans. So now we got down from 21,000 to 186. But that's over 3 days. That's 62 scans per day, and that's still too much for a SOC analyst to handle, for the fact that he's very bored in looking at port scans, like 60 port scans per day. So still unmanageable. So let's go forward. So of course there's probably, in this mix, there's some valid servers or valid applications which are providing services over several ports. So when we look at the information that we have and the destination profiles we have, we could actually see that, okay, there's 3 machines that we can now take out, and we are left with 6 sources, 95 destinations, and 102 port scans. Still quite a lot, but 6 sources is something we can start with, and 6 sources is something we can actually investigate. Now, we take the 6 sources and we take in the endpoint context. What is in the endpoint causing this information? The first one was a Linux machine. We saw that based on its network behavior, the user who was associated with that traffic was admin. Kind of interesting. Second one was a Windows machine using Nmap from the endpoint information, and Jane was responsible for that one. And the other ones, Kali Linux, another Linux, and a couple of Windows machines running PRGT. This is automatically fetched from the endpoints utilizing our agentless technology from the Windows machine, the Linux information we gather from the network, to figure out and give your analysts a faster way to triage these kinds of alerts. Then we actually go to the triage view, where we actually see how this is behaving, and this is actually how the product looks like. So the user or the analyst has an easy way or easy time actually to analyze what happened. Is this normal or not? You can mark it as normal or resolved or whitelist stuff if it's something that's normal, or continue investigations and take actions on that endpoint if needs to be. And you can pivot to other machines, what kind of alerts and information we have in the same user interface from these. So the outcome was that the first one was a network scan, admin credentials used. Second one, non-IT user using Nmap, kind of strange. Network scan, so during a pen test, Kali VM. The third one was a Forest Scout counteract server, and the bottom 2 were PRGT network monitoring, so probably valid stuff. That was after the human did the rest of the triage based on the information we presented them, and then they took action. First 3 were not so authorized, the last 3 were authorized and whitelisted. So we got to the point that it was actually actionable. So we started with 42,000 alerts, port scans, with IP addresses, no additional context, impossible, overwhelming to take action on. And with the automation of the tool, without any human interaction, we got to the point that we only had 6 hosts that we needed to investigate with the tool, with the human, and it's more actionable. Usually what we say that Magnifier produces 1 alert per 1,000 endpoints per day. So instead of your IPS system causing tens of thousands of alerts, we give you 1 alert per 1,000 endpoints per day. And how this actually everything works, in the beginning I mentioned Palo Alto Networks. We started as a firewall company. The firewalls at the same time as they are firewalls, being as physical or virtual ones, they also act as the sensor which sees the sees the data and logs the traffic into the logging service data lake over there. This creates the baseline which Magnifier does on the cloud, and then if we need the endpoint context, we have our agentless technology from Pathfinder to gather that into the same alert triage view which we saw, so the human take action. And of course, with the platform, we can of course offer you as well the ability to take response by blocking access to domains, URLs, or IP addresses. Thank you. Any questions?
Superb presentation. Compliments. I like how you delivered it. It's not just software doing some mumbo jumbo, but case by case, what do we do? Narrow down to those 6 issues, etc. I like that. I have actually plenty of questions. Now, one of them is, will you still be available at 5:30 p.m.?
Today? No.
Yeah, okay, I thought so. So you won't be able to make it to the panel. That's why I'm going to ask this question right now.
Sure.
Now, the example with the Twitter shows the creativity of cyber criminals. It's clearly thinking outside the box. Now, my question is, how can CIO imagine a threat that a tweet can kill his server? He's probably not even on Twitter, right? He just knows what it is. How do we train people to create rules for what we don't know yet? Because more data won't help, machine learning won't help, it does only what it's trained for. We didn't train that. We didn't train those Twitter tweets. It's a broad one, but...
it's a good question. I think it's a very wide question, and there's probably a lot of good answers on that one. But I actually have to disagree with you on that. It's impossible to create that kind of a rules because you never know what's going to happen. That's why the product I was discussing today actually used unsupervised machine learning. Because the problem with supervised machine learning is that if you teach it to find a door, then it's only good for finding a door. But if you think about behavior, it's like comparing behavior to physics or math. It's like a constant, it doesn't change. Behavior is something that you are. If anybody has seen the latest Mission Impossible movie, there's actually a good metaphor there. The guy had to walk through a tunnel in a certain way to behave exactly like the guy that was actually authorized to do that. And then they figured out he cannot do it. So they had to hack the system to make it change. But that, I think the same thing applies here. You cannot think so much out of the box that you could actually train somebody to do that kind of rules. You need to use unsupervised machine learning is a good start, and actually add some bit of a twist with some learning there. So we call it semi-supervised machine learning. Semi-unsupervised machine learning.
Semi-unsupervised machine learning. Okay, do we have questions? No. I think they are quite happy and satisfied with how you delivered what exactly the soft does. Okay. Here's a nice little souvenir package from our organizers. Thank you very much for your presentation, and a little certificate to hang on your wall. You were here, yeah. Okay. Harri was here. Okay. Thank you. Nice applause.